All right, 7.3 and 7.4 is today's section. And if you were good in Algebra 1, then you'll like this section because it's basically a review of y equals mx plus b, slopes, rise over runs, and all that kind of stuff. But we're going to start with a review problem from last semester. So it says the image of ABC after a rotation of 90 degrees clockwise about the origin is DEF. So the image is DEF. That means the pre-image was ABC. So the pre-image was here, then it rotates 90 degrees and you get your image. So we want to know which statement out of those four is true. So I'm going to give you a minute to look at the four statements and see if you can pick out which one you think is a true statement. Okay, so is BC congruent to DE? Okay, so BC is right here, and DE is this one. So you're telling me that when you rotate this down, BC is not going to land on top of DE? Where is it going to land? On EF, right? So yeah, that's definitely not a true statement. What about number 2, AB congruent to DF? If you rotate this down, then AB is going to rotate to DE. Yeah, so that's not going to be congruent either. So that's not a true statement. Angle C. So here's your origin. Here's where you rotated it. Angle C is right to there. And angle E is right to here. Is that a 90-degree rotation? No, not 90 degrees. Where would angle C actually rotate to? So you're saying that angle C would actually rotate down to F. Does that look like 90 degrees? Yeah, that's your 90-degree rotation. That would be a 90-degree move. So if that's not true either, then the one that's true must be letter D, or number 4 here. Angle A is right here, angle D is right there. Does that look like 90 degrees? Yeah, that is a 90-degree rotation. So this is called an isometry. Remember that word? It means one shape lands on top of the other perfectly and they're all the same size. That's isometry. Okay, so D was your solution. All right, here we go. Section 7.3, 7.4, slope is 7.3, linear equations, 7.4. So, and they're pretty quick. And this is not much, nothing to write on this slide. I just wanted you to see a few things, to remind you of a few things. You name a vector using the components change of x and change of y. Okay, that's how you name a vector. Remember, you want to find out how far you go to the right or left. That's your change of x. How far you go up or down, that's your change in y. That's how you find a vector. Now you need to distinguish the difference between a vector and a slope. Okay, that's the key thing that we're looking at here. A vector is giving you direction. A vector is like a little treasure map telling you to go over 6 and up 2, or over x and up or down y. That's what a vector is. And it always follows alphabetical order. It's an x and then a y. The slope is always going to be looking at, and you can look at the vocabulary right here, the slope is looking for steepness. How steep is that line? So it's going to go up first, and then it's going to go over, because it wants to know how far are you going up or down to find its steepness. How steep is this line? So your slope is always going to start with the y value, the rise value. So it's basically rise over run when you're talking about slope. It's your change in your y coordinate over your change in your x coordinate. So if you notice, rise over run right here for slope, the slope of a vector would be its rise over its run. So if we move that down to here, you can see that the change in y would go on top, the change in x would go on the bottom. That's how you get your little formula. Do you remember this formula from Algebra 1? y2 minus y1 over x2 minus x1. Slope, and slope, the letter for slope was m. Y equals mx plus b, the m was your slope. So this formula gets us our slope. It's also the change in y over the change in x. So if you look at your component form, now this picture's from yesterday. Remember we went over 5 and up 5? To get my vector, I gotta go over 5 and I go up 5. To get my slope, I'd want to go up 5 and then over 5. So up 5 and over 5 would still give me a slope over here of 1. The slope is 1 because I could go up 1 and over 1 and I'd be on the same line. You notice how vector has to go from the beginning to the end. A slope, you can just go up 1 over 1, up 1 over 1 as many times as you want to. It doesn't have to go from the beginning to the, I don't have to do 5 over 5 to get my slope. I could just do 1 over 1 to get my slope. A vector, you have to do from the beginning initial point to the end, the terminal point, to get your vector. Slope you can do anywhere on the line. You can find the slope any section, any part of the line you want to do, you can find the slope for. So that was just a little thing for you to see. Let's take a look at the first couple of problems here to see if we can just remember how to find slope. It says graph each vector on the same coordinate plane and then find each slope. So we're going to graph each vector. Okay, notice where it says vector. It doesn't say graph the line. It says graph the vector. What is a vector? What's a vector? What's the little guy? He's got direction and magnitude, right? A vector has direction and magnitude, but it has a beginning and an ending, right? It goes in one direction and it stops. So it starts here at negative 1, 4. A is at negative 1, 4. Okay, we'll call that point A. Actually, let me use a black pen so you can see it a little better. Negative 1, 4. And then B is at 4, 0. So here's 4, 0. So if you have an ID card or planner or something that you could draw a straight line with, you should get that out and draw a straight line. It makes things a lot nicer. Now in algebra, when we graph lines, they went on forever in both directions. And lines do. Lines go on forever in both directions, but vectors do not. And right here it says graph the vector. So you see what I did on my graph? I started at A and I went to B. Let's put A and B. And I drew an arrow from A to B. It just made a straight line and then I stopped right there. I can't put arrows on both directions and I have to have an ending point for a vector. Now they want us to find the slope of that vector. So to find the slope, I want to see my change in Y over my change in X. Now I could use the y2 minus y1 over x2 minus x1 formula if I want to. Because I have 2 points right there. I could just plug those in and get my slope. With a graph, I could also count. I could count 1, 2, 3, 4 down. 4 down. Which would be negative 4 for my rise. And I could also count 1, 2, 3, 4, 5 across. I could count 5 across, which is 5 for my run. So I could count 4 down, which is negative 4. I could count 5 across, which is a positive 5. And I would get my slope over here, which is a negative 4/5 slope. Negative 4/5 slope. If I used my little formula here, y2 minus y1 would be 0 minus 4. x2 minus x1 would be 4 minus negative 1. I make those both pluses, and I'm still going to get a negative 4/5. That's not going to change. Counting it is easier if you have a graph. If you have a graph, I don't want to do the math. I just count over and down, and I got my slope. I just got to make sure I go from one point to another point. So counting it would be better on your graph. If you don't have a graph, then you could just plug it into the formula. All right, so that would be letter A, negative 4/5. Now somebody asked me last period, Do I leave it as negative 4/5? Or could I change it to negative 0.8? Okay, with our section that we're talking about, coordinate geometry, you're going to probably want to leave it as a fraction. Because now it's telling you the direction. It's telling you the slope is you're going to go down 4 and over 5. So it's giving you those two amounts, down 4 over 5. You don't need the 0.8. Now, it's not wrong. It's the right value. It's just, I would rather leave it as a fraction. All right, letter B. Let's graph this one. E is negative 3, negative 4. Negative 3, negative 4. That's letter E. And then F is negative 3, 2. So my vector is looking like this. That's the vector this time. That would be from E to F. So what kind of slope do I have there? That's straight up. Does it have a slope? So what do I put? Zero slope? No, not zero. Not zero. Not infinite. I know you're close. It's undefined. It's undefined, or you could actually put no slope. Undefined or no slope. To have a slope, you've got to be able to walk on it. You can't walk on a wall unless you're Spider-Man. So that has no slope. Okay, the straight up and down, no slope. So vertical lines have no slope. And you can put in parentheses undefined if you want to. Okay, letter C, 3, negative 1. And 5, negative 1 is H. So that would be G and H. And that's my vector this time. Okay, so what kind of slope does a horizontal line have then? Vertical lines have no slope. Horizontal is 0. You're not going up or down. You are going exactly flat. This floor that I'm standing on has a slope of 0, so it's flat. I'm not climbing, I'm not dropping. I'm just going straight across. So horizontal lines have a slope of 0. Those are the ones that are 0, not the vertical lines. You can't have vertical and horizontal both being 0. So only one of them could be 0, and that's the one that's flat. So there's your 0 slope. Okay, letter D doesn't give us 2 points. It gives us 1 point. It says the initial point is 2, 3. So over 2, up 3. That's my initial point. We'll call it X. Doesn't give us a letter, so we'll make up a letter. Now the U is a vector. Vector U right here. So vector U is 1, 3. So am I going to go to the point 1, 3 and draw the vector? No. What's that vector telling me to do? Over 1, up 3, because it's not a slope. Slope would be up and over, but vectors are over and then up. Vectors are always the change in X and the change in Y. So the vector is telling me to go over 1 and up 3. So we'll call that point Y, and we will make our arrow there. So what's the slope of that line? The slope of that line would be 3 over 1. 3, rise 3 and run 1, so it's going to have a slope of 3. So you can put change in Y over the change in X for any vector to get slope. That's how I got the 3 over 1. I put the change in y on top, I put the change in x on the bottom, so 3 over 1 gave me the 3. In this case, it's 3 over 1, which equals a 3. Alright, how are we doing there? We good to go? Alright, let's look at the next one. This one's a pretty quick one. Now, I did give you a little picture over here. Kind of a fun little picture. Kind of illustrates the slopes. Downhill slope, if you're a bicyclist, you would like downhill slopes. You would like negative slopes because you would get to just go wee down the slope. That's so easy. If you're a cyclist, you probably don't like positive slopes because positive slopes are going to always go up. Now, when would you like a positive slope? When would a positive slope be a good thing? What about if you're a business owner? When do you want a positive slope? For your sales or your profits, right? You want positive slope for that. So there's a lot of times where you would want positive slopes, except maybe when you're riding a bike. Smooth would be the horizontal slope or 0, and he's falling because he can't ride up a straight up and down slope. So that's undefined or 0 slope. I mean no slope. Okay, so draw a line with a slope of 3. Okay, so this time it's a line and not a vector. It's got a slope of 3. It passes through the point -2, -5. So over -2, down 5. And it's got a slope that's 3. So that means we're going to go rise 3 and run 1. Now, do I just make one dot? Just go up 3 and over 1? Could I do it again? Yeah, you can do it as many times as you want to because it is a slope. So it's up 3 and over 1, up 3 and over 1. I could do it enough times to where it's easy to line up my dots. So we'll line these up. And there's your line. Where does it touch the y-axis is what it's asking. It says, where does it cross the y-axis? Y-intercept. Y-intercept equals a 1. So that would be the point 0, 1. And we have a letter for y-intercept. We call it b, little b like this. You probably remember the slope-intercept form y equals mx plus b, and that's what we call the y-intercept. Little b is the y-intercept. So that y-intercept would be at the point 0, 1. Okay, medical instruments should be sterilized for 10 minutes at 140 degrees Celsius. The machine that sterilizes the instruments has a graph of -1/2. So a graph of -1/2 means the slope is -1/2. Now on the left side on our vertical y-axis is all the temperatures. You know what this little cut right here means? It just means I didn't start my graph right up here at 0. Because I didn't want to list all the numbers from 0 to 130 in there. The graph would be a lot of blank areas. So I wanted to start with 130 here, and then I could work my way up. So that's a little cut. Now on the bottom, we're going to use minutes, and we're going to go by 2s. So 2, 4, 6, 8, 10 minutes. 2, 4, 6, 8, 20 minutes. 2, 4, 6, 8, 30 minutes. And so on. So we'll just leave the 10, 20, 30 minutes there. We'll just go by 2s. How long should instruments be sterilized at 135 degrees Celsius is the question. But the information that we need is up here at the top. 10 minutes 140 degrees Celsius. Let's find that dot on our graph. 10 minutes, 140 Celsius. So 10 minutes, 140 Celsius. Make that dot at that one. At 10 minutes, you've got to you got to have 140 degrees. So if you're in a hurry to get an instrument sterilized so that you can use it again, then you need to put your machine at 140 degrees Celsius and have it in there for at least 10 minutes. And then it'll wipe off any bacteria, viruses, whatever. Nothing could live through that. 10 minutes, 140. If you're not in a big hurry, you could lower your temperature a little bit, but you'd have to leave it in longer to make sure everything got sterilized. Okay, so it just depends on how long you want to keep it in for and what degree temperature you have to put it at for that length of time. The graph is a -1/2 slope. So that's telling me to do what on my graph? Down 1 and over 2. So I need to go down 1 degree and over 2 minutes. So for me on this graph, I'm going to go down 1 degree. 2 minutes would actually only be one line because I numbered by 2 minutes, didn't I? So I'm actually going to go down 1 and over 1 because 2 minutes represents one line on the graph. So this really is down 1 degree and over 2 minutes. Down 1 degree and over 2 minutes. So if I connect those, now this one represents more of a ray because it could go on farther unless we have an ending point. The ending actually could be a vector. The ending point could be when we get down to the y-axis. And the question says, how long should they be sterilized if it's 135 degrees on the machine? So you look at 135. Go across. We go across 135. And that point is at what minute? 20 minutes. So 135 degrees, we would need to have it in for at least 20 minutes if you want to make sure it's completely sterilized. That's how a graph can help us out. If we have our slope, we can draw the graph in and then use the graph to find our amount. And that's all for the slope section. 7.3. Done. The last one is about equations. Y equals mx plus b, things like that. So that probably will be another review part for you. Now, scenarios like this, Leon uses a pump that fills a tank at 10 gallons per second. That's really fast. That's a big hose. 10 gallons, think 1 gallon of milk. 10 of those gallons of milk each second. So that's pretty fast. Before he starts the tank, it already has 500 gallons of fuel in it. You can show the relationship between the tank and the fuel by a table, a graph, or an equation. You could actually use any of these 3 scenarios to help you show your amounts in how the tank, fuel, and seconds match up. So let's start with the table. At 0 seconds, how many gallons would the tank have in it? 0 seconds, it will have, it starts with how many? 500. Already contained 500. Says it right here. Already contained 500. So 500 is where it starts at 0 seconds. When he gets there to turn on the hose, it's already got 500 gallons in it. After 10 seconds, how many gallons of fuel then would it have? It's going to have 10 gallons every second, and we went 10 seconds. That's 100 plus the 5 that was already there. 600 gallons now. 20 seconds. That's another 100 gallons. So now it's 700. You see the pattern developing. And 800 would be 30 seconds, and 900 would be 40 seconds. So let's draw that on a graph, because we can show the relationship between the fuel and the time on a chart. We can also show it on a graph right here. So let's graph these points that we just made in our chart. 0, 500 would start right here. 10 seconds, we went up to 600. I went by 5s on the bottom, so go over 2 that gets you to 10 seconds, and then go up 1 line because each line represents 100 gallons. And then 20 would be 700. And you could actually stop there and just draw in your line. That will be a ray. That will go on forever. You could have that tank turned on forever if you wanted to. Of course you wouldn't, but you could, and that would just go on forever. So that would be a ray. Okay, so there is your graph of the scenario, how they relate to each other. You can see that positive slope. That means that as the pump is going, the gallons are going up because it's a positive slope. Now we could also make an equation. Y equals mx plus b, where y, in this scenario, the y represents the fuel. The y is how many gallons of fuel is in there. What does the x represent? The time, the seconds, right? So the fuel equals the slope. The m is our slope. Slope times the time, and then plus the y-intercept. B is the y-intercept. X represents the time. So let's make our equation. Y equals, we're going to leave x and y in the problem. Y equals, what's my slope? Up 100 over 10. If I go up 100 and I go over 10, it's going to be 10 when you reduce that, right? So it's going to be 10x, and then where does it touch the y-axis? At 500. So plus 500. Now this one is a ray because you can't have a negative time, so you're not going to go both directions infinite, just a one direction. Now the reason that an equation comes in handy is because now you can figure out numbers that are bigger that don't fit on your graph. How long will it take the pump to run to fill 3,000 gallons? Where am I going to put that 3,000 in my equation? For the y, because it's the fuel. So the y is going to be 3,000 equals 10x plus 500. So let's solve that for x and see how long it'll take. See the time. So subtract 500. You get 2,500 equals 10x. Divide by 10. X is going to equal 250. Now, would you tell somebody, oh, it's going to take 250 seconds to do that? You would convert that to minutes, right? How many minutes would 250 seconds be? Yeah, if you divide that by 60, because there's 60 seconds in a minute, you get it'll go in 4 times. So 4 minutes would be 240 seconds. So you'd actually have 10 more seconds after that. So 4 minutes and 10 seconds would be the amount of time it would take for 3,000 gallons to be in that fuel tank. So that would be an example of a linear table, a linear graph, and a linear equation. All stuff that you did in Algebra 1. Just wanted to review it again because when we talk about coordinate geometry, we talk about shapes and stuff that are on the coordinates. And that's what these lines are, these rays are, the vectors. All that stuff are on coordinates. They all have slopes. If it's a line or a vector, it has a slope. So we need to figure those things out. Okay, point slope formula. If you know the slope of a line and a point on the line, you can find the equation by using what we call the point slope formula. And here it is right here. And I like this one the best. Just my personal preference. You could just use y equals mx plus b all the time. But if you want to get it in the y equals mx plus b form, this point slope formula actually works really well. So what we have here is we have Find the equation of a line with the slope of negative 3. That's my m. And it contains the point negative 3, 4. That's my x1 and my y1. So I'm going to plug into formula. I'm going to plug all three of those things into the formula. This one and those two. We're going to plug them all into the formula. The formula is right here. Y minus y1 equals the slope times x minus x1. So I'm going to put y minus, and what's my y way over there? 4. 4 is my y1. My slope is negative 3. X minus, what's my x1 in that point? Negative 3. You got to be careful because you're going to get a double negative when one of your coordinates is a negative inside of your point. So I'm going to end up with a double negative. I'm going to make them both pluses. All you have to do now to get y by itself is just distribute and then move the 4 over. So we're going to distribute this 3, negative 3x and negative 9, and then bring down your y minus 4, and then add 4 to both sides. So you'll get y equals negative 3x minus 5. All we did from here is get y by itself. That was our goal there, is to get y by itself. Once you plug it into the point, you can just simply get y by itself, and you'll have your equation. Now, that's not the only way to do this. You don't have to know this formula. If you want to, you could start with y equals mx plus b right away, because that's what you're trying to end up in, right? Y equals mx plus b. You could actually start there. You could plug in the x, the y, and the m. Just right here, you got x, you got y, you got m. So I could put 4 equals negative 3 times negative 3 plus b. And I could try to solve for b since they didn't give me that in the problem. And I get 4 equals 9 plus b. I would subtract 9. And I get b equals negative 5. Then I have to put that negative 5 in for b in my equation. So I'd have to put y equals negative 3x minus 5. I plug in my m, I plug in my b, and I have my slope-intercept form. It's the same answer. Okay, you're going to get the same answer either way, but you kind of have to solve and then plug in over here. Over here, you're just solving. After you plug in the original numbers, you're solving. Here, you got to plug in the original numbers, solve, and then plug it back into the original equation. So you're plugging in twice on this side. On this side, you're plugging in once and getting your answer. So that's kind of why I like this point slope form a little better. But again, it's up to you. Bless you. Okay, so we could also use the point slope form when we have parallel equations. Parallel lines have the same slope. It's written there for you. Parallel lines have the same slope. So if I've got a line parallel, that means I know I need the same slope. And what's my slope in this equation? 2. So I need a new slope that's also going to be 2. Because the slopes have to be the same. So that means my new equation is going to start with y equals 2x. It's going to just have a different number for b back there, plus b. I don't know what the b is yet, but it's got to have a different number. It has to have the same slope. They both have to be 2's. My point here is the x1 and the y1. So I would use my same formula. Y minus y1 equals m x minus x1. I would just plug it in and solve it. Instead of having to plug it in twice, I just plug it in the once and solve it. So y minus the y1 is 4. So it's y minus 4. The m that I need to use is the 2. That's my slope that I have to use because it's a parallel slope. So I'm going to put 2 parentheses x minus the x that I have to use is a negative 2. And now that I've got it plugged in, I can just Distribute and solve. That's it. So you're going to distribute here. You're going to make those both pluses. So y minus 4 equals 2x plus 4. Add 4 to both sides. And I get y equals 2x plus 8. So that would be my answer right there, that equation. Now, why is it important to get that 8? Why couldn't I just add 2x plus 7? Because it would be parallel. It would both be 2x. That'd be 2x. That'd be 2x. It would be parallel, but why do I need that 8 there? Why does that b have to be 8? Because it has to go through which point? Negative 2, 4. If it doesn't have an 8 here, it's not going to go through that point on your graph. It'll go through other points, but it won't go through the one you want. So you got to get the right b with the right slope so that it'll go through the point that you need. So that would be the answer that would go through that point, and it would have a parallel slope. Now perpendicular works exactly the same way, except how do we get a perpendicular slope? Well, they're right here. Opposites and reciprocals. This is a test. You test it by seeing if they have a product of negative 1. If you multiply two slopes together and you get negative 1, then you know they were perpendicular slopes. You know that they're going to make 90-degree angles. So in this case, I need a perpendicular line. So I need an opposite and reciprocal slope to a positive 2. So what's going to be an opposite reciprocal slope to a positive 2? It's got to be opposite sign, so it's got to be negative, and you got to flip it. So it's got to be negative 1/2. So negative 1/2 would be my opposite reciprocal. Let's test it. 2 times negative 1/2. If I put a 1 under this 2 and I cross cancel, I'm going to get a 1 because it's 1 over 1, but I'm going to also get a negative because they're different signs. So it does test out to be a perpendicular slope. So negative 1/2 is our slope. This is going to be my m. This is my x1 and this is my y1. So I'm going to use my same formula, y minus y1, m times x minus x1. So all I'm going to do is plug them in once and solve it, and I have my equation. So y minus the y1 is a 4 again. M is negative 1/2. X minus, and x1 was negative 2. Again, double negative, so make them both pluses. Distribute. So you get y minus 4 equals negative 1/2. And then these 2's are going to cancel. Right, so you're going to get a negative 1. And let's add 4 to both sides. So that cancels out. You get y equals negative 1/2 plus 3. And again, we need the 3. We need this 3 because we want it to go through that point right there. If that's not a 3, then that's not going to go through that point right there. It'll still be perpendicular. It'll just be somewhere else, and it won't be on that point that we want. So the negative 1/2, oh, I forgot the x, sorry. Negative 1/2 x plus 3. Negative 1/2 x makes it perpendicular. That 3 makes it go through that point. So that would be perpendicular slopes. Last one is a scatter plot. So let's look at the scatter plots. We're going to kind of move quick on this one because we're running low on time. So, scatter plot is when you see if there's a relationship between sets of data. We want to see if there's a relationship between the latitude and the temperature for certain cities around the world. Is there a relationship between where its latitude is and what the temperature is? So let's look at it. Beijing, 39.9, we'll round that to 40 at 35 degrees. So make a dot. Beijing, we're going to start down here at 40. We're going to just go to 40 because 39.9 is about 40. We'll go up to 35 degrees. London is 51.5. 51.5. So let's see, 51 amps, just past the 50, and it's up to 44. So there's 40, 45 there, so it's just a little bit below 45. That'd be your London. Mexico City, 19.4 is the latitude. So that's just before the 20, and it's up to 66. 65, 66 is just above it. So almost at the point 2065. It's just a little teeny bit above that and to the left. Miami has a latitude of 25.8. 25.8 is the latitude. So that's just past 25, and it's 75 degrees in Miami. That's the average temperature in January. That's not much for that. 75 degrees. Nairobi is negative 1.4 latitude. That means it's pretty close to the equator, because equator's in the middle, negative 1.4 would be just below it. So negative 1.4, so it's going to be really close to zero, just on the left side of zero, and then up to 77. So that's just above the Miami temperature. Actually, we put that a teeny bit higher. Right about there. And let's see, Quebec is 46.8. 46.8 is the latitude. 46, 45, 46 is just past the 45. And then it's up 19 degrees. So just below 20. Right in that area. And then Rio de Janeiro, negative 23.0 degrees latitude. So negative 23 would be close to negative 25. And then it's 84 degrees there. That's a nice temperature too. 84 degrees would be way up in that corner. Rome is 41.9 degrees latitude. So it's just past the 40 and up to 54 degrees. So just below 55. And San Francisco, 37.8 is the latitude. 37.8 is just past 35, or kind of in the middle there. And it's up to 56 degrees. 56, right around there. Pretty close to the other one. It's 54. And then Sydney, Australia, negative 34 degrees. Negative 34 degrees would be close to negative 35, or negative 30, negative 34 is like right in the middle there. And up to 79 degrees. So like right about there. And then Tokyo, 35.7. 35.7, that's going to be pretty close to 35, just a little fast. And 48 degrees. Right about there. Okay, let's get rid of this. Don't need that anymore. Okay, so there's your scatter plot. So it wants us to see if there's a relationship or a correlation. Does it look like there's any kind of relationship there? Well, doesn't it look like it's kind of coming downward, right? Kind of. So basically, the farther you're going on the latitude, the lower your temperature is going. So it's kind of a negative correlation. It looks like it's going downward. Now, a line of best fit. So it says approximate a line of best fit. Approximate means it doesn't be perfect. But a line of best fit usually has about the same amount of dots on both sides. So if I'm looking at this, I'm thinking a line of best fit might be somewhere in this area. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4. So might be over a little bit more. Maybe more like this. In this area, we got 1, 2, 3, 4, 5, 6, 3, 4, 5. We could actually put one of them on the line. And then you'd have 5 on both sides, right? You have 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. So that could be an approximate line of best fit. What you'd then be looking for is some points that are on that line. And again, these are estimates. So for me, I would look here, and I'm going to use red, and I might say, okay, this, I could consider maybe that's a point on the line. And maybe I look down the line and I consider, okay, maybe that's also a point on the line. And I can look and see, how did I get my slope? What is my rise and my run for this slope? So in my slope, I would go down, and each one of these represents 5 degrees. So 5, 10, 15, 20, 25 down, 5, 10, 15, 20, 25, 30 degrees latitude across. So it's 25 degrees down, and it's 30 degrees across. So my slope would be negative 25 over 30, but we could reduce that slope. It's going to be a 5, 6, yeah. So negative 5 over 6 would be my slope. One of my coordinates that I could use either one. This coordinate is 10 degrees and 70 degrees. 10, 70. That could be my x1 and my y1. So with a point and with a slope, I can plug it in and get my equation. So y minus 70 equals negative 5, 6, x minus 10. So I'm going to get y minus 70 equals negative 5, 6x, and negative 5, 6 times 10 would be a positive 50 over 6. And I can reduce that, if I will, in a second. Let's add 70 to both sides. So let's see, y equals negative 5, 6x, and we could change 50 over 6 to 8 and 1/3. Because 6 goes into 50 8 times with 2 left over. 2 6 would reduce to 1/3. And then 8 plus 70 would be 78 and 1/3. So that would be where your y-intercept would be. It would touch up here at 78 and 1/3. So the y-intercept would be 78 and 1/3. Now on this graph, the y-intercept is this line right here. So this is where 0 is. So my 78 and 1/3 would be right up here. So that's the y-intercept.